Good morning, Calculus 1. Welcome back. We're in the middle of Chapter 3 here. I'm moving into this section 3.5. The title is Implicit Differentiation. Implicit Differentiation. And so let me try to explain this word, this new word here, implicit. All the time we've been working, we have y as a function of x. So another way to say that is y is explicitly written in terms of x. So we have y by itself equals x squared, e to the x side. Y is a function of x's. Y is explicitly written in terms of x. Y is by itself, like this. Y equals 3e to the 2x plus tangent 3x. That's an explicit function. We've been working with a lot of explicit functions. So what's going to be new is trying to work with implicit relationships. By the way, when they're implicit, I can't use the word function. I might slip up and do that because we have situations like this, where we have x squared plus y squared equals 25, where x and y have an implicit relationship. So nobody is solved for anybody. X is not solved in terms of y, and y is not solved in terms of x. We just got x's and y's all mixed up, and they have an implicit relationship. Cool. By the way, y is not a function of x. This is kind of a classic circle here. So this is not a function, but anyway, just because it's implicit doesn't mean it's not a function, but oftentimes it is not a function. When y is explicitly written in terms of x, it's often a function, should be a function. So when let's go back up here. When I take this derivative of this explicit function, you might think, I'm doing the derivative over here, I'm doing the derivative to these I'm using all my rules over here on these guys. But in a way, you are doing the derivative of this y, and you're calling it y prime. Or if you don't mind, you're doing the derivative of y, you're calling it y prime, or if you don't mind, let's call it the derivative of y with respect to x. So that's kind of what we call it. Anyway, and we are doing the derivative of the y with respect to x, and that's our notation. Then we go over here and we do these derivatives with respect to x, and everybody knows how you do a derivative of an e function. The 3 sits there. The derivative of the e function is just himself. The chain rule spits out a 2, a multiplied 2. Everybody knows plus. Everybody knows how to do the derivative of a tangent function. It's secant squared of 3x. The chain rule says you have to do the derivative of the little 3x, spits out a 3. So I could write that 3 in front of him. I could write that 2 in front there. I could clean that up a little bit. But we just did an explicit derivative like we've been doing. Okay, now watch this. Now we're going to walk into this implicit relationship, and we're going to do an implicit derivative. So here we go. Here we go. So here's how we do it. We walk into each term and we just do the derivative of each term. And when we do the derivative of an x term, it's just kind of a normal derivative. The derivative of x squared is a power rule, 2x. But when we do the derivative of a y term, we treat it like a chain rule. So here's what that means. You do a power rule. Oh, I got to do the 2 times that y to the first. Now you have to do the derivative of the y. And since we're doing it with respect to x, the derivative of a y with respect to x is called y prime, or dy dx. Now listen to me, if I wrote y prime right here, it's easy to lose that little prime and get a little confused. So I tend to, it's correct, but I tend to use the dy dx notation when I'm working on implicit functions, so I can keep, because that's the derivative right there. Dy dx is the derivative. And it came out as the derivative of that y after you did the power rule. It's sort of it could be thought of as a chain rule situation. Let's go across the equal sign. Anybody know the derivative of 25? The derivative of 25 is 0. So we did the derivative, but again, where's the derivative? The derivative is this dy dx. So what we do then is we solve for that. So we're going to do algebra. From here on, it's algebra. You move the 2x over, 2y dy dx equals a negative 2x. We divide by the 2y, so dy dx is, when I take the negative 2x and divide by 2y, the 2's cancel. I get a negative x over y. And that's the derivative. That's the slope of the tangent line. Notice, it's implicit. The derivative itself is not explicitly in x's. The derivative itself has x's and y's mixed up. So that's the slope of the tangent line to this circle, to this implicit relationship. So I tried to explain it as best I could. Let's try a more complicated one here. This one's quite a bit more complicated. So what did I say? You walk in and you just walk into the equation, you start doing the derivative. Again, you're doing the derivative with respect to x. So when you run into any other variables that aren't x, you got to do a little chain rule. Maybe that's a good way to think. But when I walk into this first 3x squared, that's just a derivative with respect to x. That's easy. That's 6x. When okay, here comes a new idea. When I walk into this 4xy, technically that's a little product rule. Technically it's a little product rule. Let's try it. I'm thinking of the 4x times the y. Let's try it. If it's 4x times y, let's see, I'm taking the derivative of the 4x. That would be a 4 multiplied by the y plus, now I'm writing down the 4x, and now I'm taking the derivative of the y. Well, when you take the derivative of a y with respect to x, it's dy dx. I mean, you could think of it as a 1. When you take the derivative of an x, it's just a 1 with respect to x. When you take the derivative of a y, with respect to y, you might call it a 1, but with respect to x, you call it a 1 dy dx. Here we go. I moved to the next term. So that was this generated this little product rule here. Next term, the derivative of a y squared. Oh, you just do the derivative normal, 2y, but then you multiply by a dy dx. That's one way you can think. You could say, oh, I'm just going to do the derivative rules normal, but when there's a y term, I'm going to tack on a little dy dx. That's cool. I think that way of thinking might work. What you're doing the little chain rule. You're doing the derivative of the little y there with respect to x and spitting out the chain rule. Let's go to the other side. Equals, the derivative of the x is a 2. The derivative of 2x is a 2. The derivative of a y cubed is a 3y squared. But then I tack on a little dy dx. Ta-da! We just did this implicit derivative. Now what's complicated is, where's the derivative? It's the dy dx, so it's kind of all over the place in here. And what we want is we want to solve for it. So the rest of this is algebra, and some students get lost in the algebra. But what I want is I want to solve for dy dx. The strategy is get everybody with a dy dx on one side, get everybody without a dy dx on the other side. Then we'll factor out the dy dx and divide by that stuff. That's the algebra strategy. Let's try it here. I already got, let's see, so let's get the dy dx stuff on this side. So I got the 4x dy dx. I got the 2y dy dx. I'm going to move this over here, so that'll be a positive 3y squared dy dx. Equals, I'm going to move everybody else to the other side. There's already a 2 on that side. I'm going to move this negative 6x and a negative 4y. And then in order to solve for dy dx, you factor it out. I'm left with a 4x plus 2y plus 3y squared equals this. And then you divide by that. So dy dx is this monstrous implicit derivative. It's 2 minus 6x minus 4y all over this. 4x plus 2y plus 3y squared. Wow. Cool. I don't know what this is. It's kind of a complicated, I don't even know what kind of graph it is, but with the y, I got a feeling it's not a function. I got a feeling it's some kind of a graph that twists and turns around itself. It fails the function test. But what we found is a formula for the slope of the tangent line at any point. If I had a point xy, I could fill in the x's and y's and I'd have a number. I'd have the slope of the tangent line at that point. That's what we're doing. Let's go back here. I want to go back to this problem. I had this circle. Let's say I wanted to find the equation of the tangent line, at a certain point. Let's say we're at the point 3, -4. So, by the way, I'll just get a little picture of that here. This is a circle centered at the origin, radius 5. If I plug in the point 3, -4, it does satisfy this. 3 squared, -4 squared, that's 9 is 16. That does work. Where is that? That's right about here. So over 3 and down 4. So it's a rough picture, but I'm looking for the equation of that tangent line. You know, I did the derivative implicitly, so I have the slope of the tangent line right here. This is the slope at any point, x, y. So if I'm at the point 3, -4, let's see, I can plug that in. The derivative would be negative x over y, which is a -4. Okay, so the slope is 3/4. That's a nice positive slope. I guess that is what my picture looks like. And I want the equation of the tangent line, of course. So that means I take my point and my slope and I usually do my point slope formula. Y minus the y value equals the slope times x minus the x value. I'll just clean that up. That's a y plus 4 equals, I'll distribute this, 3/4 x minus 9/4. This is a y plus 4, so I'll subtract this 4 over here. Subtracting a 4, I'm working my way into a corner, but the equation of that tangent line is 3/4 x, what am I doing? Let's get a common denominator, minus 25/4. Cool. All right, there may be a couple other cool things to say about this. Implicit derivatives, they're cool, they're important. So good luck. Thank you.